or they are an even number. What I mean, the bits which are in error for the length of the block you have considered is more than 1. It's not able to correct the errors. Or rather, if it is even, because if it is more than 1 but it's still odd, it can detect that, but it can't detect if. So it's able to detect 1 error, or um, 3, I mean, or you can detect multiple bit errors so long as they are odd. So because of that, we have a more powerful error detection technique, and this is the CRC, cyclic redundancy check. Again, this is a very simple algorithm. It's powerful, but a very simple algorithm. In this case, just like in the simple parity, we are taking a block of bits, and then we are subjecting it. I'll use the word subjecting it to some process where we have um, another block of bits, which are used as um, the generator pattern, a predetermined pattern which is being used for generating what you are going to transmit, rather what, and whenever what we generate to transmit, we normally refer to it as a code word. Yeah. So our main aim is to generate some code word, and actually for this case, we normally generate the CRC, some code, a short code, which we concatenate to the message we want to transmit. So I hope we have passed here. So what we are doing here is we have our message in M bits, and I think our example here, the M, like an example here, we are taking 6 bits. Our M bits are 6, and then our pattern is 1010. So when you put it in terms of bits, because sometimes we may not put in terms of bits, we may call it just generator polynomial with this represented as, and I think we did that as polynomials, and we said that the ones and the zeros, the bit positions are placeholder. I mean, we can have polynomials as placeholders of these bits. So if you have, and I think we looked at that, so we said this can be represented as x to the 3 plus x. Yeah, these two. Yeah. So sometimes you may be asked specifically to work out your CRC in using polynomials. Yeah. And kindly, if you ask to use polynomials, do not use binary. Yeah. So in this case, what we are supposed to do, we are supposed to get the message, then we add the as many zeros as this, as the power, or rather the degree of the polynomial, the degree being the highest power. Number of zeros equivalent to the degree of the polynomial. So because this polynomial is, the degree is 3, so you're going to add 3 zeros. That is one way of looking at it. The other way of looking at it is if this pattern has got 4 bits, then you add 3 zeros. But actually what it means is that we are simply multiplying in the polynomial form. We are multiplying this with the highest, with the degree, with the highest, with x to the power of 3 to the x to the power of the degree of the polynomial, which is the highest element, is element with the highest power. So never forget to do that, because I've seen it's very common when people are asked to calculate, because they forget what is the n minus 1 number of zeros. If n is a number of bits in the pattern, in this pattern of zeros and ones, and of course you get the wrong answer. So what you are supposed to do, you are supposed to get this, add the requisite number of zeros, then do long division of, we divide the message concatenated with the number of zeros, you divide the pattern with the pattern. Yeah, I think there's a simple case here. I think the simple case here we seem to have, I think I pointed that out last time. And this is 1010, but I think in our division we have used something a bit different, 1101. So there you have, our pattern has 4 bits, so we consider that to be n plus 1 bits. In that we like using n to refer to the length of the CRC. That's why so you are seeing this is n plus 1, so that n is the length of the CRC. So this CRC is a remainder. Sometimes we use the word CRC, we use the remainder, it means the same thing. We also call it the FCS. Yeah. That word comes, that means frame check sequence. Frame check sequence. And it mainly comes because this method is used mainly at the at layer 2 of the OSI model. Yeah, it is a point, we call it the data link layer. It happens at the data link layer, and the packet in that layer is called a frame. Yeah. Later in that part, we are going to look at the networking models. We are going to look at that OSI model. So that name frame comes from that, because it's normally used to check whether the frame has an error. So sometimes we call it the FCS, sometimes we call it the remainder, sometimes we call it the CRC. So in this case, we do the long division. The long division is here. It's straightforward division, long division of binary. You may also be asked to do long division in the polynomial. Yeah, long division with the polynomials, but in this case we have done it in binary. So this is your original message. We have added 3 zeros because this has 4 bits. Then we divide with this, we get 1. I'm sure we are all familiar with this long division. So we have 1101. 1 plus 1 is 0, is XOR, no carry. 1 plus 0 is 1, 0 plus 1 is 1, and this of course is 0. So we take from where the 1 starts is what we take. So we will take, we will not, when 0 is on this side, we ignore it. So we start from here. So there is 110, which you can bring this bit down, and this bit we have brought down is 0. So 1100 divided by this, it becomes 1101, and so this is 1. In binary, plus or minus is the same. So we in binary maths. So this is 1. Then you bring 1 down. If you can't divide 1101, you put 0. Bring 0 down. You still can't divide this, you put 0. Then you bring 1 down. I mean, bring this 0 down. When you bring this 0 down, it goes once, and you remain with 0 and 0. Now, this one is interesting because it is a CRC. Has to have 3 bits. In this case, you see, you have brought when you bring this, you have to remain with 3 bits. So, if, for example, if this was you have to include this 0 here, so that you have the 3 bits. Once you bring down the remainder, you always have 3 bits. So you have to include this 0. Yeah. For the remainder, you use the 0. Of course, I said when you're dividing, you don't consider the 0. But for the remainder, you have to have 3 bits. So once you bring this down, you have 2 bits. You have to consider this 0. So the remainder is 0 and 0. So what you are actually going to transmit is this message concatenated with 0 and 0, the remainder. So that's what is transmitted, and what would happen is you have the CRC generator at the receiver, and we have a CRC checker. We have a CRC generator at the transmitter. Then we have a CRC checker at the receiver. And what the CRC checker does is it does the same arithmetic, because this will have been shared. This pattern will have been shared between the receiver and this pattern. It will have been shared between the receiver and the transmitter. Yeah, it will have been shared either maybe as overhead, but it will have been shared. So the receiver is going to take what it has received. It has no idea what it is. Yeah. So what it does, whatever it has received, it carries out the same operation. Now you do the long division of so in this scenario, let's see what we are going to get when we do the long division. So now we have 1 0 1 1 0 1 0 1 0. This is what we have added. This was the original message, and we divide with the same 1 1. Oh, something has moved. 1 1 0 1. So this will go once because of 1 1 0 1. That is 0 1 1. We bring 0 down. It goes again once because of 1 1 0 1. So we end up having 1. So we bring out the we had brought out the 0. We bring out the 1. So we bring out the 1. It becomes 0. We bring out the 1. Bring out 1. It becomes 0. That is 0. Then you bring out the 0. It becomes 0. Then you bring out the 1. So 1, 1. So when you bring out the 1, this becomes 1 because of 1, 1, 0, 1, and you remain with 0. So how this works is, if you get 0 as your remainder at the receiver, it means the bits which are received are the same as the one that was sent. If any of this change, if any of this bit change, and you can try that, then the remainder will not be 0. Yeah. But this one does not check only one bit. Yeah. We will not get into it, but it can be shown that actually this can, depending on this pattern, because again, what we are doing, we are not generating the pattern, we are just using a pattern. We are doing the basic thing of using the pattern. Otherwise, ideally, you are supposed to generate your own pattern depending on what you want to attain. Do you want to check single bit errors? Do you want to check all errors up to the length of the? So again, you have to choose your pattern. But in this case, what we are concentrating on is just generally how it works. So we have that pattern, but generally you can get an idea of how. So you need this, your pattern to be this. It should not be divisible by x. It means actually you cannot use this pattern which I had mentioned somewhere here. You can't use this because this is divisible by x, because this is simply x cubed plus x. So this is divisible by x. So you can't use this polynomial. You can't use this pattern which is equivalent to this polynomial, because it will not be able to check errors. So one of the most important things, it should not be divisible by x. It should be divisible by x plus 1, which means to be divisible by x plus 1, it must have this format at the end. It has to have x plus 1, like this one. So this one is x to the 4 plus, x to the 3. X to the power of 3 plus x to the power of 2 plus 1. So this should be divisible by x plus 1. I think so. I've not tried to divide it, but I think it's divisible by x plus 1. It should be divisible by x plus 1, which means very likely the last element, the rightmost element, must be 1. Yeah. So for this, if you are to use polynomial operations, you can do polynomial division. So in this case, if here P is equal to this, let me see what I've called P. So this is the MX. This is our message. Yeah. Sorry about that. That is M. So that is a message. Okay. And our P is this. Yeah. This is the generator polynomial. So that was a message. So what you do, this is MX message. That was the problem. So our message is this. So concatenating with these zeros is actually simply multiplying by this first element here, the x to the power of 3, x to the degree of this polynomial. So you multiply by x to the power of 3. That is equivalent to adding 3 zeros. So that you are going to get x to the power of 8 plus x to the power of 6 plus x to the power of 5 plus x to the power of 3. So that is what we have. The division again, always have at the back of your mind that what you're dealing with here is these are position holders for the binary. So it is like binary addition. It is similar to binary addition or GF2 addition. We are going to see that later. So you divide this with this, it can go x to the 5 because of x to the power of 8 plus x to the power of 7 plus x to the power of 5. So again, you subtract. If you add x to the power of 8 and x to the power of 8, that is like you're adding 1 plus 1. Yeah. So this becomes just 0. X plus 7 comes down. X plus 6 comes down. X plus 5 and x plus 5 is 0 again. So x to the power of 3 comes down. So it can go how many times? X to the 4 times. So we get x to the 7 plus x to the power of 6 because of this, and x to the power of 4. Yeah, this times this to the power of 4. So this becomes 0, this becomes 0, this becomes x to the power of 3 plus yeah, this becomes to the power of 4. So it becomes x to the power of 3 plus x to the power of something is not right. Okay. Oh, it's all right. This becomes x to the power of 4 plus we remained with x to the power of 4. Sorry about that. We remained with x to the power of 4. So we bring down x to the power of 3. But there's an x to the power of 3 here, which I'm not understanding. Oh, this was there's something wrong with my math here. This x to the power of the second is x to the power of 8. I think here is where
I think it is x to the power of 7.
X to the power of 7 here. This x to the power of 7 plus x to the power of 6 plus x to the power of 4. Yeah, that is that. Oh, I think it's because we had brought this down. We had already brought it down. I think at the beginning, we should not have brought this down. Yeah. Yeah. So you divide by this becomes x to the power of 4. So we have x to the power of 4 and plus x to the power of 3. I was thinking like I'm bringing 2 of these. So x to the power of 3, so this becomes x to give us x to the power of 4 plus x to the power of 3 plus x. So this cancel out and we end up with x. So our final code word, the one we are going to transmit, is x to the 8, or is this x to the 8 plus x to the 5 plus x to the 3. That's our original message. And in this case, concatenation is just adding the remainder, which is x. And actually, this x is the same as this. The same as this 0 and x. I mean 0 and 0, because this represents x is a placeholder for this position. So this is the same as this x. So you get the same thing, whichever method you use. Yeah. So you can either do it with this, with binary, or do it with this. Um, we use polynomials. And you can see that not being divisible by x guarantees that all burst errors of a length equal to the degree of polynomial are detected, and being divisible by x plus 1 guarantees that all burst errors affecting an odd number of bits are detected. And this, you can see all of them are divisible by x plus 1. They have this 1 here. So this is CRC 16. And I think this one is used by Ethernet, where you have 16 bits. Yeah. Then there is CRC 32. So that is CRC 32. So you can see the CRC 16 has got only 4 elements. Yeah. And this one has got, so not all of them are there. Yeah. And of course, at the transmitter, that's what happens at the transmitter. At the receiver, you should do your division, and eventually it should give you 0 when you do your division. And when it gives you 0, it means there is nothing changed during transmission. So that is error detection with CRC. So it can be shown that the following errors can be detected. These are all single bit errors, all double bit errors, any odd number of errors. So it all depends on how you choose your generator polynomial. That's the most important thing. So we are not, for this we are not getting into the generator polynomial, but you'll see later that when it comes to BCH codes, you can actually generate your own generator polynomial depending on what you want to achieve. Yeah, it's part of the design of error control. Error correcting codes. So, does anybody have a question on error detection? Yeah, and this difference with error correcting codes. So, whenever you talk of error correcting codes, we're actually talking about codes that can both detect and correct the errors. So, we use that word error correcting codes. So, again, for error correcting codes, which we are saying we have to use, especially where we expect errors to happen. Because what happens is if you have a lot of errors, then, or where the bit error rate is very high, or you expect the bit error, the probability of error is very high, or what you call bit error probability, rate probability, then you don't use error detection, because what will happen is there will be a lot of retransmissions, and eventually you're not going to get anything through. It is better that you add enough redundancy such that the error is corrected at the transmitter, at the receiver, sorry. Otherwise, you risk having a lot of retransmissions, yeah, whenever there's an error. So for systems like the wireless systems, because of interference by other transmissions, wireless transmissions, we normally prefer to use error correcting codes. Yeah. Satellites, we prefer again error correcting codes, and mainly apart from the probability of errors, is the fact that the transmission, or rather the propagation time is the propagation delay is so high. So you can imagine if you are having a lot of retransmissions, that will take a lot because a lot of time. And imagine you send a packet, yeah, for the case of satellite, where you have your ground station, then you have your uh, satellite, and then you have another ground station. Maybe you are leasing a satellite link, and you have got two offices. You have one office in Kenya and you have another office in Atlanta. Because actually, this is one of the nowadays with the fiber we don't bother, but before fiber, that was the main way of communicating with offices which are remote. It was the cheapest, especially where it is not practical to have terrestrial communication like either terrestrial microwave or cabling. Yeah, so satellites was the only way out. So you can imagine you have this, and I think we agreed when I was introducing that things have changed nowadays because we have Elon Musk's um, satellite, which works with the LEO, low Earth orbit. So propagation time is short because most of the systems we used to have to avoid the problem of of handoffs, too many handoffs. Yeah. Handoff is what happens, for example, with GSM or 3G, generally with mobile. You are in a moving car, you keep on being given to other base stations. So that process we refer to as a handoff. So you're going to have, if you have a lot of handoffs, but in the system where old systems, we wanted to make sure that the satellite we are using is completely stationary with respect to the Earth. So that is the geostationary. So, and if you calculate geostationary with the speed of light, you're going to find, and that's the speed of light in a vacuum. So, in this transmission through the atmosphere, and of course, the speed will even be reduced. So, we are talking about 100 microseconds one way. Yeah, your signal to get to the satellite, you're talking about 100 microseconds. And then I think I tried to explain that in this satellite, actually this is a transceiver. The satellite is a transceiver. It means it gets a signal. Sometimes it will be transmitting at a different frequency, which actually means is you get the signal, demodulate, get back to your baseband signal, then modulate again at a different frequency and transmit. So there will be maybe another 20 microseconds. Actually, this is 20 milliseconds. So even just take it microseconds, which is unlikely it could go to maybe 200 microseconds or 0.2 milliseconds. Then take another 100 microseconds. So this is about 200 milliseconds. Even if you ignore these microseconds, we're talking about 200 milliseconds. Then do what? You look through your data at the receiver and establish that it has an error. So you don't send any acknowledgement because whenever there is an error, it means there is no acknowledgement because we normally don't send negative acknowledgement. We assume there's no acknowledgement, there's an error. So this one has to wait for acknowledgement. Yeah, and it has to wait for another 200 milliseconds. And if there's no acknowledgement after 200 milliseconds, it has to wait for another few milliseconds to conclude that I'm not waiting for any um, acknowledgement. So there's normally a timer circuit. So the timer has to be set more than 200 milliseconds, maybe 250 milliseconds. That's when you retransmit again. So you can see there's a lot of delay. So this system would not be adequate for satellite communication, would not work very well with satellite communication. There will be too much delay. So with the satellite communication and main also with wireless, generally wireless communication, you find that actually the system that the codes that are used are error correcting codes. And I think I said from the beginning, whenever you talk about code, it is referring to what you get out after you subject your data to either generate a polynomial or generate a matrix. What you get will refer to a code. So the code refers to all the possible code words. Yeah. Because again, digital communication works with what are we expecting? What is the range of the signals we are expecting? Which are all the possible code words? We are going to find that when we apply when we start encoding the data to get the code word. So another correcting code, which we also refer to a forward error correction code, is a system of adding redundancy to a message. Remember, even for the detection, we are still adding redundancy. But generally, for you to be able to correct the errors, you add a lot of redundancy, enough redundancy to help you recover your message at the receiver without reference to the transmitter. So in this case, you don't require a return channel. So broadcasting also falls in this. Apart from bad channels, we also use it where we don't have a return channel at all, like broadcasting, one-way communication. So the block codes fall into those two categories. Well, error correcting block codes, yeah, fall into two categories, and one is well, I think error correcting codes fall into two categories, yeah, the block codes and convolutional codes. But where I was talking about the error correcting, because even the ones for detections are actually still blocks. They work on blocks, yeah. But here we're referring to the error correcting block codes. So you can either have the block codes or convolutional codes. And we are going to look at both cases of block codes and also of we are going to look at the case of block codes, and then we are going to look later at the case of the convolutional codes. An example we are going to find of block codes are Hamming codes. Nothing special about Hamming codes. They are just a certain, it's just block codes that satisfy certain certain relationship between the error checking bits, the message, and the code word. Yeah. So we are going to say that. And please remember the message. So if you decide your message is that, when I say your message is this, what I'm saying is if you decide your messages are 4 bits long, because the message has to be the same length. And you decide to subject this to some generator matrix GX, and you receive something like maybe that. Yeah. So this will be the error checking code which you have generated with this generator matrix. So you refer to this as a code word, this as a message bit, and this as a error checking bits. Yeah, what you have added, what you have generated. Like the other case whereby we are concatenating, this one, when you subject this to generator matrix, it gives you something like this. And we are going to see this as a special case of what we call block codes, but it's a special case of block codes. It's block codes which are systematic. Systematic means you have your bits and then you add your error checking bits. Because sometimes it may not produce something like this. The bits may be mixed. The error checking bits may be mixed with the message bits. Yeah. But anyway, this becomes very clear once we begin doing examples. It becomes very clear. So this is a case of the error. This is a case of a block code, and in this case, we are looking at a simple case where we are dealing with a systematic code. So this is the n-digit code word. Yeah, these are the k message bits, and these are the nk error checking bits. So these k bits can be any size, but we are seeing cases like the Hamming code. The Hamming codes, these message bits are a certain length, but there can be any number of bits, and you subject them to the generator matrix or generator polynomial, and if you check like this, like what you are going to do with is basically what we call a linear block code. Yeah, this is a binary linear block code. So you are saying if it's a binary, if it's a linear binary block code, then we call it linear if the modulo two sum of two code words is also a code word. So, and we are saying that the block, there is a block code given here. This one, this is a block code. We're using this generator matrix. So we are going to see how this generator matrix is related, especially for this systematic code, how is it related with the one for checking. Remember in the other case, like the CRC, we're using the same pattern both at the transmitter and at the receiver. But we are going to see that with error correcting codes, the generator matrix is normally very different from the error checking matrix at the receiver. Yeah. So the code we are talking about is this code. And the way we have generated this is we are multiplying these messages. Maybe you can call them, these are the bits, D1, D2, D3, and D4. Okay, yeah. So we are getting those digits, we can call them M1, and then we are multiplying with this. Yeah. We are multiplying, like for example, let's see. get a simple example. Let's look at this. 1100. So we are multiplying this with 1100. So we are multiplying, and you can see this is a row vector, and this is a matrix with both with the n rows and n minus k, no, and k columns. Sorry, just n rows and k columns, and it makes sense. So sorry, it has n columns and k rows. Yeah, and it has to make sense because for you to be able to multiply the matrices, the number of columns here must be the same number of rows here. So this is a row. This is a row vector, which means is a, how do you normally name vector? I mean matrices. We start with the rows first, the columns. Yeah. Yes, Amolo. You raise your hand. Omolo. Alfonso is Omolo, not Amolo. Omolo. Yes. You have a question? Or it was by mistake? Okay, we assume it was by mistake. So if you multiply these two, if you multiply, so what you do is actually you multiply each before you transmit. You multiply each message with the generator matrix, and then you get a code word. So what you transmit is not the message, is the code word which you have received by multiplying this message with the generator matrix. You can see that the message, if you have 4 bits, what we are saying, if you have 4 bits, the only possible messages you can be sending are these, are 16, because 4 bits can only be organized in 16 ways. So if your message was 5 bits, then you can combine that in 32 ways. So for this case, the maximum is 16. So whatever message you have, it will be one of these. Yeah. And we are saying when it is one of these, if nothing goes wrong, whatever will be received is one of these. And you can see these are the only possible 16 messages if there is no error. So the other possible, which is 128 minus 16, because you have 7 bits. So 7 bits can be arranged in 128 ways. But only 16 are what we call valid code words. Only 16 are valid code words. The other 112 are not valid. So in the next class, which is tomorrow, we are going to look at the concept of valid code words and how you detect a valid code word at the receiver, and therefore, and what you get if your code word is not valid, which means there's an error, which means something has changed. Yeah, it means it is not one of these 16, and it is only this 16. You see, the moment these are your messages, and you subject this to a particular generator matrix, then that is the only possible signal that was transmitted, and therefore at the receiver you are trying to find out whether what you have received is any of these. It's a very simple concept and yet a very powerful concept in error control in digital communication systems. So as usual, just post your registration number on the chat. As we post numbers, if you have a question, you can ask. Yes, Samuel?
Yes, it's not really a question, but a suggestion.
Yeah.
If maybe time allows,
Mm.
over the many years I've been studying, I've realized I'm more of a, myself personally, I'm more of a sequential kind of learner. I
Yeah.
get a bit overwhelmed when I usually find it easier to understand concepts quickly when we kind of do it like the way we used to do it last sem in the physical class that we had, where you were explaining to us, I think it was DFT. Now when we do it together, we do the computations, we do the divisions, I usually find that kind of approach, to me, I usually find it easier and faster for me to get concepts. I don't know if the rest would agree. I don't know if maybe if time allows, you could go through a few examples in that kind of way.
Sure. We are going to do examples. The only thing I was wondering is whether we 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 will need to be it needs to be physical, because if you agree it's physical, we will do it physical. Yeah, because I think it was a request from your class that we do it online. But for me, it's okay. If you'll be okay with the physical, still we can do physical. But definitely we are going to do quite a number of examples with this. Not even the learning itself will be with a lot of examples, and later we can even look at more examples. Yeah, is that okay, Samuel?
Yes, thank you.
Yes. But as a class, you can decide whether you may want some physical classes. I'm game. So if there are other questions, then we'll see you tomorrow at 8.
Excuse me, sir.
Yes, Oduor.
Okay, I just wanted to seek a certain clarification,
Yeah.
even as others are leaving.
Yeah.
I've noticed that in most of these live streaming sites, like YouTube and Netflix,
Yeah.
they embrace error detection techniques,
Yes.
but they don't do so to the error correction techniques. Now,
Yeah.
my question would be that does error detection techniques necessarily require an error correction technique, or like do we need and for every error detection do we need an error correction technique?
Yes. Actually, yes, you are right. When you use error detection only, what you are saying is if there is an error, then you don't attempt to correct the error at the receiver. You ask the transmitter to retransmit. So what will happen is, and I think like today, most of these systems are through fiber. So even the designers, when you have systems that go through the fiber, you don't expect errors. So you are saying in the event that an error happens, you can just drop that packet and ask the the transmitter to retransmit. Our fear of using uh, error detection only is where you have a lot of possibility of errors, because then you're going to have a lot of back and forth. Retransmit, see there's an error, retransmit, then you end up never transmitting any information. So most, especially whereby you are more sure about the bit error probability, yeah, of that channel, then you'd rather use uh, the error correction, I mean error detection only, and then ask for retransmission. Why is because error correction normally you add little redundancy, but for error detection, but for correction you add more redundancy. As we are going to see, like now you can see we are talking about a 7.4 code, almost 50% is error correction bits. I mean, is error checking bits, because 4 are the message bits, 7 is a code word. So the difference in 3 are bits you are adding only for the purposes of error correction. So, and that is overhead. So can you imagine if you have got you are transmitting a movie and you are employing this error detection, this kind of this error correcting codes, it means you have to use much more bandwidth to transmit the same information. 74 is a lot. Yeah. So you can see why most people would prefer to use error checking unless they are compelled by either the number of errors being too many or there being no return channel. Because always, if you want to get your data without errors, it means you need you need to get an acknowledgement. And in the absence of an acknowledgement, then we retransmit. Yeah, after maybe some time, because you only know there is no acknowledgement after the time you expect acknowledgement to come has expired. And again, we are going to look at that. It's one of the things we are going to look at when we come to the third part of this unit. We are going to look at what we call flow control. Yeah. So I hope I answered your question with so many words.
Yes. Indeed.
Okay. So thank you very much. Then we meet tomorrow morning at 8. Have a good